All right, chapter 2. This is going to be a little bit of review. And let's see, before I get started, I'll eventually need these kits, model kits.
I just ordered one yesterday.
Okay.
Is that good? Is that still okay?
Oh, yeah. That's for you to keep at home. This is what you use when you're here. And I'll let you know when we need them. And I'll tell you what, I better get one too. We'll all build a model together. The first part of this chapter is just going to be review. So if there's anything in here that you haven't seen before in general chemistry, let me know and we'll stop and hash it out. Remember the VSEPR theory, valence shell electron pair repulsion. That's the way we determine structure. One way that we can determine structure. And the first thing you have to do, of course, is to draw the Lewis dot structure. And then identify your central atom and say how many groups of electrons are attached to it. So lone pairs count as one. Single, double, and triple bonds all count as one group. So if you had something like this, a carbon there and maybe an oxygen there and a hydrogen there and a chlorine there. There would be three groups around that carbon. So the coordination number would be 3. And that's the one that tells you the geometry. A 3 coordination number, 3 equals trigonal planar. And the bond angle here is 120 degrees. Okay, that's where we're going. So when they say, I know my general chemistry textbook doesn't speak in terms of groups. It actually uses the acronym VSEPR, valence shell electron pair repulsion. It's not electron pairs that we're interested in. We're interested in the groups that are attached to the central atom. So in this case, you'd have 2 pair, but you don't count them separately. You probably already know that. Okay. And of course, you know that after you draw the Lewis dot structure, and it has to be a valid structure, then you give it the electronic geometry. That includes all the lone pairs. And then to get the molecular geometry, you just cover up the lone pairs and see what's left. Right. For instance, ammonia. You have a hydrogen in the back, a hydrogen here, that forms a triangular base. You got a lone pair here, and overall, that's tetrahedral. Electronic. But if you cover up the lone pair, what do you got? Well, this is at the apex, and these are at the corners of the triangle of the base. So you have a triangular pyramid. Okay. Remember that? Okay. Hurry, hurry, hurry. I catch it in time. Okay, we're still up. Sometimes I forget to plug in. My battery runs down. Okay, so now that we've established molecular geometry, these are reminders of what do you get when you count the number of groups. And remember, the geometry is around a central atom. So if it's a simple molecule, it could just be one single geometry for that molecule. But if it's a complex molecule, like a lot of organics are, then you can have a string of carbons and have different groups on them. And this one might be trigonal planar and this one might be tetrahedral. Or this end might be bent. Okay, so the geometry is around a chosen central atom, even if it's in a bigger molecule. Okay. So if you have two groups, remember that's linear. And what we're trying to do is put those bond electrons or lone pair electrons as far apart from each other as possible. And that's what these regular geometries do. If you have three, you're going to have a trigonal planar. And if you have four, it's tetrahedral. Let's see. Did it go to 5? No, it didn't. Let's go ahead and do those. All right. If you have two groups, right, you have linear. 3 groups, trigonal planar. 4 groups, tetrahedral. 5 groups, you have a trigonal bipyramid. You have this central triangle, and then you have something up here and something down here. So if you draw the connecting lines, all that gives you a trigonal pyramid on top and a trigonal pyramid on the bottom. That's what that means. And then 6 would be octahedral. It's like this one, only instead of a triangle, you have a square. Then you have your central atom, and then something connected there and something connected there. So that's where we're starting from. Now, if each one of these positions, let's see, if every position is occupied by an atom and it's bonded to the central atom, you'd have no lone pairs. Then what are the possible bond angles? This one's obvious. It's 180 degrees. Right? Okay. Trigonal planar, the bond angle, if you go here, here, and here, go all the way around the circle, that's 360 degrees. You just divide it into 3 and it's 120 degrees each. So this bond angle is 120 degrees. Tetrahedral, I gave that one to you yesterday. 109.5. Trigonal pyramid is a little different. If you have a central atom here, and then you've got some other atoms here, there, 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 and there, what are the possible bond angles? Well, if you go from here, if this is the apex of the angle, then you go here to there, that's a right angle. But if you go here to here, that's on the trigonal part, that's 120 degrees. So you can have 90 degrees and you can have 120 degrees. And if you want to go to the extreme, you go from here to here, is 180 degrees. So those are the 3 possible bond angles for that geometry, as long as every position is occupied by an atom. If we had a lone pair up here, then that 180 degrees would go away. It wouldn't be there because there's no atom. Okay. Are you scratching your brains?
Once I look at that, yeah,
Oh, okay.
Yeah.
Okay.
it's a little rusty, that one. Yeah.
Octahedrals,
Yeah.
if we have an atom at each corner here and each apex there, then if you go from here to here to here, that's a right angle. So all these are right angles. And if you go from here to here to here, that's a right angle. And then there's 180. So octahedral could have possibly a 90 and a 180. Okay. So in order to determine the molecular geometry, you have to find out where the lone pairs are. And that's where the Lewis dot structure comes in. It tells you where your lone pairs are. And then from the lone pairs, cover up the lone pairs, then you can determine the molecular geometry. And I think that's the next slide. If you have two groups, all right, no, if you have two atoms bonded, all right, this is set up a little different than I'm used to. If you have two atoms bonded, obviously it's 180 degrees. But if you have two atoms bonded and there's an extra lone pair, you got a bent molecule. If you have a tetrahedral and you have two lone pairs, you still have two bonded atoms, but it's also bent. All right. The one on the far right, the tetrahedral with two lone pairs, that's water. Water's your best example for that one. Trigonal planar, if all the positions are occupied with atoms, and if you have one lone pair, then you have a trigonal pyramid. That was the ammonia that I showed you. What if you have two lone pairs? That's bent again, right?
Is it not more than it's two?
Yes, right. Lone pairs are not confined by a bond. So they tend to go plop, like that. And that puts pressure on the others, on the bonded electrons, and squeezes that bent angle. Say for water, we start with 109.5, but water is probably 107, maybe less.
That's where it starts to get a little tricky. Do you need to, like, do we need to have anything particularly memorized for that? For those, when you have that, those two lone pairs where it's not really an exact.
Once we get to our pure carbon discussions, then if you have to memorize anything, there'll just be a few of them. That's the nice thing about organic chemistry. You don't use inorganics unless you have to. And lots of times the inorganics that enter into a reaction are used for catalytic purposes or to activate a site on a molecule. I'm thinking of a Grignard reactant. We put electron withdrawing groups on a carbon like this. It's got something else out here. But we put an electron withdrawing group here, right? So it's polar that way. What that does is it depletes the electron density around the carbon and gives it a slight positive charge. So if the other reactant comes in there and it's got an excess, it's got maybe lone pairs or it's a negative like that, that's where it's going to attack. And we enhance the probability of the attack coming there by introducing that group. And that's called a site activation. All right, we'll talk about that later. Okay. See, so I can see what I'm doing here.
Will we ever really see the signal off pyramid or off the people?
Not an organic.
I was gonna say, because I'm not really understanding that whole thing.
That's probably why they didn't put it in here. They didn't put the 5 or the 6 groups.
So I really don't even need in my notes.
You would have got it in first semester, general chemistry.
But we can not really think about.
I don't think you're going to need it though. I just wanted to be complete. Yeah. I think that's why those are focused on, because we're still talking about carbon. Okay, so if we have ethane nitrile, which is also acetonitrile. Ethane nitrile is the proper IUPAC name. So you have ethane, 2 carbons, and the side group is a nitrile. That's the triple bonded nitrogen to the carbon. Yeah. Let's see. The other one, acetone, is that's the trivial name. Propanone is the correct name. Whenever you see an ONE on the end, you've got a carbon with a double bonded oxygen on it. And something here and something there. So ONE means that. If you have a chain like that, and this last carbon is bonded to an OH, that's an alcohol. And the ending of the name is going to be OL.
Will you say the meaning of, again, it's
It's this
carbon,
carbonyl group here. Carbonyl. It's just that identifies a carbon attached to it with a double bond to an oxygen. That's a carbonyl. Okay, what's the point of this slide? Oh, it's just showing different bond angles. Yeah. The one on the far left is linear. Then the one in the middle is trigonal planar. And the one on the far right, the carbons are all tetrahedral.
Would you mind if I sent that this? Like right there? It's like when you write on the board, like your back is and it's kind of blocked.
Oh, you want to sit right here?
Either that or just write that computer.
Oh, yeah, sure. I don't use this computer anyway. Maybe that's why it's protesting. Give me so much trouble.
Yeah, that'd be a lot better. So let's see.
Okay. All right. So actually, we mentioned the effect that lone pairs have on the central atom geometry is they tend to, well, in the VSEPR model, they create for you the electronic geometry so that you can, that tells you the approximate location of the atoms that are actually bonded. Because if you don't have the lone pairs, then you have one geometry. If you have lone pairs, then they enter into our VSEPR model, and that positions the other atoms someplace. That's the purpose of knowing where the lone pairs are. So, let's see, those carbons. Let's make some room now. What do we have here? 2-amino-ethanol. Ethanolamine. Okay, 2-amino-ethanol. So I'm just going to draw it, our line drawing. Like that. This is an oxygen with a hydrogen on it. And then this one is an amine group. Yeah. Notice that nitrogen likes to have 3 bonds. And when it does, it still has a lone pair, just like ammonia. Remember, ammonia was like that, and it had a lone pair when you draw the Lewis structure. So same thing happens here. It's got 2 hydrogens and 1 carbon bonded to it, still got that lone pair sitting up there. Okay. It's in organic chemistry, it's also wise to know who has lone pairs and where they're located. Because lone pair electrons speak to that first condition. Understanding organic chemistry is, what are the electrons doing? And if you have some lone pairs, you better know where they are, because they're going to enter in somehow. Okay. That'll become clearer, I hope, once we get to the drawing the arrows, showing where the electrons move. Okay, so this is a carbon, that's a carbon. So this is, it would be ethane, but it's an alcohol. So we say ethanol. Okay. And if this carbon was attached to 3 hydrogens, then that's all that would be, just ethanol, right? The kind that you put in beer and booze. But now we have attached that amine group. Okay, now we're getting into a little nomenclature that I may be stepping on my own toes here. But when you identify this parent chain plus this active group, the all, that automatically makes this one. Because it's the carbon attached to the OL.
I had some trouble with that on this. I
Yeah.
was counting some, yeah, okay, that makes sense.
And then this one's 2. That's why this one is 2-amino ethanol.
And since those are only 2 carbons, that's just your parent chain.
Yeah, this is the parent chain. And another thing I noticed is when you're counting your finding your parent chain, once you hit a non-carbon, you stop counting.
Yeah, I didn't do that. I counted did nothing.
And that becomes a side group.
And then like like here on one of these, for example, I had, this is a clear ethyl now, but I didn't stop counting.
Yeah.
I think that's where I'm having trouble is like deciding like which is the parent chain, but it's like a side chain, like when it's like that. So like I would probably count oxygen as a part like 1.
No,
And then I guess that's where my confusion's really coming from.
only carbons.
Okay.
Only carbons are parent chain.
Okay.
And there are only 2 carbons in this molecule. So it has to be derived from ethane.
Okay.
Let's see. Okay. So the point of the slide then was saying, what's the geometry around this nitrogen? Electronic geometry is trigonal planar because you have 2 bonds to hydrogens and 1 lone pair. So electronically, this is trigonal planar. But molecular, cover up that one. Hold on a second. Wait a minute. No. I apologize. 1, 2, 3, 4. So this is tetrahedral.
Do that one more time. The 1, 2, 3, 4.
Yeah. Well, let me draw the hydrogens in there separate.
Okay.
Now, how many groups around that nitrogen? 1, 2, 3, 4.
Okay, so you're counting the pair as another 2, correct?
For the electronic geometry, yes.
Okay.
Yes. So we got a tetrahedral electronic geometry. Now, if we cover that one up, that makes this one a trigonal pyramid.
So,
Around that nitrogen only.
so if you have a tetrahedral and you take away, well, I guess it depends, never mind. I had to think about it, but.
Well, yeah, sometimes we
Because
think out loud.
you have 2 lone pairs, and then if you took away both of those lone pairs, it would be a different shape. But
Yeah.
in this case, if you have, okay,
Just 1 lone pair.
Yeah.
Mhm.
then it will always be trigonal.
Okay. Now for this one, this carbon, it has a hydrogen and a hydrogen. So now it's tetrahedral, both, because there are no lone pairs. Right? And the same thing for this one. It's got hydrogens here and hydrogens here. So these both are tetrahedral. Okay, they're including oxygen. So when you draw oxygen, it likes to have 2 bonds, but it still has 2 lone pairs.
So would it still be tetrahedral?
Electronic tetrahedral, yes.
Okay.
And since we cover these up, it's bent. The molecular geometry is bent. I always go back to water. That keeps me grounded for oxygen. All right, so whenever you have nitrogen and everything's neutral, if nitrogen is bonded to 3 other atoms, then it's going to have that lone pair. If oxygen's bound to 2 other atoms, it's going to have 2 lone pairs. And carbon is, usually if it's neutral, it's going to be bound to it's going to have 4 bonds. It may not be 4 atoms, but it's 4 bonds. Right? Like if we had like this, there's 1, 2. So what else do we put in there? Well, let's see if we do this. Right now we got acetone. But that carbon has 1, 2, 3, 4 bonds. But what's its shape? 1, 2, 3 groups. According to VSEPR, it's trigonal planar. Yeah. Okay, and whether a molecule is one shape or the other influences what we call steric effects. In other words, if we just had hydrogens here, that would be formaldehyde. Right? And those hydrogens probably wouldn't get in the way of an attack on that carbon. If another group, something here, wanted to attack that carbon, then the hydrogens wouldn't get in the way. But these methyl groups are a lot bigger. Right? The steric effect is they would hinder the approach of that attack. Okay.
What is the steric number again?
I'm sorry?
The steric number.
Steric.
Well, yeah, that's what we always call it. We call it the steric number at the beginning, but how do you determine the steric? Steric, you just said something, but I don't remember how to determine it. You know, we would have questions. What's the steric number? And you were just counting something and then it would be the steric number.
Oh, I've never used that terminology before.
Well, you said this, you said steric there for a second.
Oh, the steric effect.
Steric. What is that?
That just means you have a greater steric effect with larger side groups.
Because it makes sense.
Yeah, because they're out there physically in the way. Yeah.
So
I think I have heard steric number before.
So I mean, if it's not something we're going to be really needing, then that's fine. But I remember
Not right away. We are going to get to that. In fact, one of the next slides, we're going to start talking about it. Now, if you have some things can happen to carbon. We're going to keep it really simple now. We're going to start with methane. And we know that's tetrahedral. But if we break off one of those hydrogens and let the hydrogen take see, it has 1 electron this side, 1 electron that side. If it takes both electrons with it, like that, what's left? Well, you're deficient in an electron, so now you have a positive charge there. That's your carbocation. And if we do the formal charge calculation, we should find out, let's say this would be 4, right?
what?
Hold on a second. The carbocation, let's do the formal charge. Right, so 4 valence electrons for carbon, right?
Yes.
Okay. And then we have 1, 2, 3. Minus 3 equals a plus 1. So that's the charge on carbon. The formal charge on carbon is plus 1. If on the other hand, say we have that methane. In this case, the hydrogen leaves as a proton. So it leaves all of its electrons behind. Right? Now we have both of those electrons standing out there with nothing to be bonded to. Okay, so then we take 4 minus 1, 2, 3, 4, 5. Now it has a formal charge of minus 1. It all depends on what we do with that hydrogen and the electrons. Does it take the electrons with it or does it leave them behind?
And how will you know that?
Experience. Lots of problems. I'm no expert.
Will we have to deal with that?
It would, actually, what I think is the problem would have to tell you, or you could see from the reaction itself where that hydrogen is going and what it's taking with it.
Okay.
Yeah. If it's going into solution and making an acidic solution, it's going in as a proton only. So that means it's leaving electrons behind. So that's one example. Okay, so what does this say about the geometry? Well, now we have 1, 2, 3. So around that carbon is trigonal planar. Okay. Now we're eventually going to talk about this later, but I just want to introduce an idea here. If that's trigonal planar, right, you got that positive charge. This one, this one, this one, those hydrogens. Try to think of it in 3 dimensions. That's trigonal planar on the plane of the board, right? So you have an attacking group that has extra electrons, because that's usually what happens. They're called nucleophiles. They go for nucleus referring to protons, positively charged, or a slight charge. It may be like this. But those nucleophiles, now that this is trigonal planar, it could easily attack from this side or that side. And if you happen to have 3 different groups attached, and it attacks from one side, you get one isomer, one stereoisomer. If it attacks from this side, you get a different stereoisomer. So probably what you'll get is a racemic mixture, 50-50. Right? And I'll define those terms later. If you haven't heard of them before. Now for this one, let's see. This one has excess. It's got 4 groups. So this is tetrahedral. Right? So it's going to be carbon, hydrogen, hydrogen in the back. Oops. Hydrogen here. And then we form that pyramid base with that. And now you have tetrahedral electronic structure.
So the more electron like group arms things, the more like protected and sound it is. Is that what? I guess I'm getting confused because you said it was like attacking, and I guess I'm getting confused.
Oh, when we're getting to reactants, say you're going to react it with some molecule over here. Where is it going to attack? Right?
Okay.
It's probably going to attack someplace that's either excess electrons or deficient electrons. So if it tries to attack this one, since it's planar, it could just as easily attack that carbon from this side or that side.
Okay.
That's all I'm saying.
Okay.
But for this one, if it's going to attack that carbon, it could attack from this side, right, and go past the hydrogens because they're really small. But it's going to have a better shot at attacking from this side where the electrons, there's no steric hindrance. So if there's an isomer, if there's a chance of making a different molecule, an isomer from this one, it's probably going to be more of it, a higher percentage of your product is going to be from that attack than from this attack. That's all I'm saying. The geometry has an effect on the outcome of the reaction. Okay. Let's see. Oh, dash wedge notation. You're going to see this a lot. Oh, you already done that before? Okay. All right. So if we have, using their example, if we have carbon here on the plane of the board, that means if it's tetrahedral, we can draw a plane through the tetrahedron that will actually incorporate 2 of the hydrogens in a method. So there's a plane here. But if it's tetrahedral, then the other 2 have to go into the board and out of the board to make the tetrahedron shape. Maybe that's where we ought to put our models together. So,
Yeah, I think once I was able to visualize that the dotted line was the one that was kind of shooting to the back.
yeah. So, black is carbon. You don't have to push those things all the way in, just far enough for them to stick. Because they're really tight.
And the white ones are hydrogen.
Yes.
We're doing a tetrahedral, correct?
Yeah, just take a carbon atom. It's already set up to be tetrahedral. Because
Or,
it's,
yeah, I meant like,
yes, that's,
sorry.
so there's your methane. And if you hold that up here, where the carbon is against the board, and these two are in the plane of the board, it would be like that. But if you look at it head on, this hydrogen covers up the one in the back. So we have to offset them a little bit. And when we do, the one that's coming out of the board, we start the small end of the wedge on the carbon and make the big end of the wedge here with the hydrogen. Then we make, we go back to this hydrogen in the back, and this is dash lines. That's what we're trying to show. Now, what if you rotate it? Rotate it, let's see, if we're like this, and if we rotate it so that the next one says, we're going to rotate it so these two are on the level and they're pointing out of the board. Right? So these get the solid wedge, these get the dashed wedge.
Wait, which one gets the dash wedge?
These guys, because they're going back into the board. And these guys,
Well,
yeah, go ahead.
why wouldn't it be, wedge, straight up and then dash?
Well, what you want to do, well, two of them are going to have to be the same because it's a tetrahedron. Right? They're either going to have to come out of the board, these two out, these two in, or if you rotate it enough, then these are in the same plane with the lines. And now this one is out and that one's in. Are there any other possibilities? Set it like that. With just this one in the plane of the board. And those two would have to be dash wedge, and this one would have to be solid
And
wedge.
now, if you were looking at it on this perspective, where this hydrogen is hidden,
Yeah,
what would you do in that case?
you wouldn't.
You would.
Because if you hide the hydrogen, then you're not showing the full geometry. Now, that's not to say that in the real world it happens. Oh yeah, it depends on your perspective, right? But
So if you're going from this way, would you do wedge, and then dash?
yeah, oh, from my perspective,
Yeah, like
those
wedge, dash.
dash,
dash.
yes,
Okay,
looking from my
Yeah.
angle.
yeah,
From your angle, it'd be the other way.
yeah. But, so what did you say about there has to be two of them? Can there not be
Oh.
one single, like,
Yeah, there can be.
okay,
If you rotate it a certain way, you can have one in the plane of the board and the others are either out or in.
okay,
Like if you do it like this, if you do it like that, it's hard to see this one in the back, but it would be a dash. And these would both be wedges, and that would be a solid line.
okay. Solid line, wedge, and then what would you do? Would you kind of put, like, if you were to draw that out, would you put the dash like directly down in between the wedges?
Yeah, make it as short as you can so that it gives you the appearance of actually being behind.
Okay,
If you draw it long as these are, then it implies that it's up closer to them.
okay, yeah, I get what you mean.
It's all perspective. Okay. Let's see. Now, I'm not sure if this is very helpful at all. For this molecule butane 2-all. There, notice that the OL is on the end. That means it's an alcohol. There's an OH group attached. Where is it attached? Well, the parent is 4 carbons, so that's butane. But we're going to attach that OH at the number 2 carbon. That's why it's butane 2-all.
Why is there no X? Why is that, the 2 sticks with the bread? Why is that, would that not be considered ethyl somewhere in the name?
Well, we gotta find the longest chain, don't we? Let's see, butane. 1, 2, 3, 4. And then we've got an OH here. Right? Okay. So you're starting with butane.
Okay, I see.
I don't keep going.
Okay, we're starting with butane. 1, 2, 3, 4. That's the longest carbon chain in the molecule. And it's going to be an alcohol. But we want the numbering to be as small as possible. So we don't start from this end, that'd be 1, 2, 3. We start from this end, 1, 2. Right, so that's your 1 carbon, that's your 2 carbon. And then we change this to all, but we say where it's located. It's located on the 2.
And we're not saying it's an ethyl because there is a separation between O and H.
Ethyl would be 2 carbons, right?
Right. But I guess I was looking at it. Just not, I'm not sure why I was.
So I don't understand. So I don't get what the O, like I get the 2 and I get the, but what is the OL? Like, I guess that's what I'm confused about.
That means this right here.
Okay.
That's
The way I'm
the,
confused why it's not OH.
that's the alcohol group.
Okay.
OL always means alcohol.
With C, connected with. the
Connected
carbon.
with the carbon, yes.
Okay. And why is it butane and not butane?
It's not, oh, why did we drop the E?
Yeah.
Convention.
Silly chemistry stuff.
Yeah.
Okay. So, but if I put it, it's okay. Like you're not going to count me wrong.
I wouldn't do it. We have to be sticklers in the beginning.
All right. I'm gonna get confused, but it's okay.
What we're doing is we're taking that E that was there and we're substituting this for it.
So when will I know to drop the E?
Whenever you add an ending on this, say we had, how about this one? Instead of the alcohol, we have a double bonded oxygen. That's going to be an ONE. So we still start with butane. But now we're going to substitute here at the 2 position carbonyl group that we identify as ONE. So the butane 2-one. I thought it would help if you start off with the E, but now you're going to substitute something for that E.
Okay. So for the E, we would just substitute where it's at, like the 1, 2, or 3. Correct.
Where it's at, what it is.
Okay.
So for the- see how it's at my butane first.
Uh-huh.
Why is it going first and not the end? I'm just asking because like on the quiz, like some of these you put like hexane at the end instead of at the beginning.
Like typically the number of the carbon, the number of.
Which number are we looking at?
I mean, kind of all of them.
Like on the quiz, say for like question 3,
Okay.
hexane is at the end. Like for that, it's at
Well, it's at the beginning because that's all there is. Now, if we substituted something else in here, say we had, let's see, let's do it on this one. Say we had a chloro. Okay. Then we would put, it's on the number 1 chloro.
But wouldn't it be 1 chlorometh?
Hmm?
Wouldn't it be 1 chloromethane?
Mm-mm. That's still butane, 1, 2, 3, 4. This, okay, I think, some students have trouble with the line drawings because that's a carbon, that's a carbon. There's not a carbon there. That's a chlorine. And that's a carbon. So you still had just 4 carbons here.
Okay.
But I can kind of see that too, because that carbon is branching off to the chlorine, but it's not considered a methyl.
Correct. Yeah, it's a chloro, it's not a methyl.
So it's only a methyl if there's nothing.
If there's nothing there, that's a methyl.
Okay,
Okay.
got it.
And we're substituting, if you want to think of it that way, say you got a methyl there, but no, we want to throw that methyl out and put a chlorine there. Right?
So I guess another thing I have trouble with is when there is a methyl on 1 or 5, like whatever the end numbers are. I guess that's when I get confused because I think it's part of the parent chain.
Well, if it's connected to the carbon of the chain, you count it. It's when it branches, you have to decide which one's longer. So if we had like this, maybe that. And then we had this, that. Then we could go 1, 2, 3, 4, 5, 6, right? 6 is possible. 1, 2, 3, 4, 5, 6, 7. 7. So your parent chain would be this one right here.
Yeah.
And then you would count, let's see, 1, 2, 3, 4, or 1, 2, 3. Well, it doesn't matter.
And then that would be the
4.
ethyl.
Right. This would be 4 ethyl heptane.
Okay.
Yeah. That's where it can get confusing if you have to, when you're counting up for a parent chain, you have to ignore the branching. Except when you have, as long as there are carbons connected to carbons and there are no interruptions like an oxygen in the middle, then you keep counting. Right? Go this direction. All right, what if we branch this direction? What do we get? You know, we found our longest one was actually off of what looked like a branch. So instead of saying 3 propyl, 3 propyl hexyl. Hexyl would be wrong because it's not the longest chain. It's heptane. Practicing a lot of these helps. Okay. Now the authors are trying to make a point here that 2 at any carbon with 4 bonds on it, two of the attachments to that carbon are going to be in the same plane. Right? Because there's only 3 involved, right? So you have a plane there. But if you go from that carbon and look at the other 2, it's a different plane. And those 2 planes form I guess they call it a V. Oh, it's just, okay. That's complicating the issue.
It's just this.
Yeah. It says the 2 straight lines are in the plane of the board. And that dictates where the other 2 go. Yeah, okay, so let's skip this one. We beat that horse enough. Okay, what do you do when you rotate the molecule? We've looked at that already. But if it would take some time to build that one. So let's just try to imagine it. If we have this cyclopentane, and we have this one is chloro, yeah. And then this one is, and this one is down here. H. It's like that. Okay, I think that's the way they drew it. What would happen if you rotated it, say, on that axis, you flipped it over like that? Well, If this one's in the back, now it's in the front. So I would draw it duct like this. Now the chloro is a solid wedge. This one and these two were out of the board. Now they're into the board. Let's see. And that means, let's see, this one, then this one was going to be, and this one's going to be that. Let's see, does it finish the example? Oh, they actually built a model. Think we should we build the model? Okay. All right. So we're going to need 5 carbons. This also gives you an idea of something called steric strain. The totally unstrained bond angle for carbon is 109 degrees when it's tetrahedral. There's virtually no strain on the bond if it's in a cyclic arrangement. Right, let's see, we need this one, this one. There we go. Usually what happens with these 5-membered rings is 4 of them are in the plane like this. Before I put my hydrogens on there, I want to show that. These 4 are in the same plane. And then the 5th one is usually puckered. That's how it relieves a lot of the strain. Because the angle in a, let's see, what would be the angle in a 5-membered ring? It's 360 degrees around. That's a good question. Better keep building. Let's see those. Okay. Wait a minute. I don't want to do that. Put these up. I want to put this one back here. And I want to put this one up here. This one. These are
Instead of
both,
the green ones, can we use the blue ones?
as long as you know what they mean. Or you can get another set if you, another kit if you want.
And then are those white ones in the back?
Yes.
So
On the 2 to the left, the 2 to the left are all white. So if you have it, if the apex is up like that, no, apex is up like that, then these 2 on the left are both hydrogens. And this one has a chlorine going backwards. Which should be, oh,
so is this correct?
let me see. What color is chlorine supposed to be?
Wait. Do all of them have? hydrogen in the
Green.
back?
Green is supposed to, I don't have any green.
Yeah, I don't have any green either.
Let me see. You asked that question earlier.
Yeah.
That's good. Wait, I don't think I want to go there. Oh, there are some.
You need more blue?
Oh, I see.
Here.
Yeah.
Yeah, you can use blue. As long as we know what they mean. Let's see. So, orient, so, okay, the way I've got it is these two on the left are
Yeah.
both hydrogens. And then on the top, we have a chlorine going backwards.
Mhm.
And a hydrogen coming out the front. Okay, got that one done. Now we got a chlorine. Okay, I put that on the wrong side. This chlorine comes out the front. Okay. All right. And then this one is the hydroxyl group, the alcohol. There. And a hydrogen on it. That. There we go. Okay. All right. Do ours look alike? Yeah. All right.
I
So,
think these will actually help me understand it a little bit better.
okay.
So,
Now what we were going to do is flip it, right? Along this axis. So if we flip it like this. Oops. My mistake. Still H. OH back, chlorine back, chlorine forward. Like that.
I guess we don't really ever put it this way, do we? I guess that's like way too complex to do. If you were to like face it this way. Instead of this way, being this way.
Oh, looking edge on?
Yeah. I guess you really don't do that.
Sometimes you do. That's a different, these are called projections. That's a different projection. And the projections are invented to facilitate the visualization of different types of molecules. Right now, we're just introducing the dash wedge convention. Okay. So now we're going to do a little more review. The polarity of the molecules. Actually, we talked about that last time already. Polar covalent bonds. Now, if you're trying to assess the polarity of the entire molecule, you do have to know two things. Are the bonds polar and are they symmetrical? If they're not symmetrical with polar bonds, then you're going to have a polar molecule. But one non-polar molecule does not behave the same way as another one does. And the reason for that is they may cancel each other out, like that central one, the carbon dioxide. Notice that you've got excess electron density at the outer edges, out by those oxygens. Okay. Overall, the molecule is nonpolar, which has an influence on its physical behavior, its chemical behavior. But when you get to looking at the interaction of molecules, you still have those negative regions on that molecule that can interact with positive regions on other molecules. Okay. So what I'm trying to say is it's not really a steric effect. It's more a subset of polarity, right? The bonds themselves are still polar, which gives you a slightly negative end for oxygens on both sides. So if you approach with something that's got a positive side on it, that's where it's going to bond. Even though the whole molecule is nonpolar, you can still access those differences in electron density. Water is definitely polar. And hydrogen fluoride is polar because there's only one bond in there and it's polar. Now, how do we determine the overall polarity of a molecule? It can be measured. You can measure the polarity of a molecule. And they're using a system here that I haven't used in a long time. The net dipole. It's 0, right? There's a scale, I guess. And you know what I'm thinking? I bet that dipole value is based upon Pauling's electronegativity scale. That topic aside, in the case of tetrachloromethane or carbon tetrachloride, you have a polar bond for every chlorine carbon bond, but they're all pointing to the apexes of a tetrahedron. They cancel each other out. Now, the polarity, according to that space-filling model, is, or the electron density model, it tells you that the polarity is not very large because you don't have any reds. So the net dipole of this molecule is going to be 0. Well, that's what they tell us it is. But if you do have a polar molecule, what that value tells you what that value tells you is there has been a vector summation of the dipole moments. So what do I mean by that? Has anybody had physics in here? No. Yeah. So you know what a vector is. It's a magnitude in a direction. Well, if you have a magnitude in this direction and you have a magnitude in that direction and they're both attached at the same point, then you can do a vector summation of the two and say, all right, those two, let's use 2 ropes pulling on an object, right? So if somebody's pulling on the rope this direction with that much force, and somebody's pulling on the rope in this direction with that much force, what is that actually equal to? So the way we do it in physics is we draw a parallelogram. This is the same length as that one, and this is the same length as that one. And the vector summation is that one, in that direction. Okay. And that's what the dipole for that molecule is saying. Once you know the dipoles of every bond, they all add up to that value. All right. So if you had somebody pulling this way with the same strength as somebody pulling that way with the same strength, they cancel out. Right? It's like tug of war. Yeah. That's vector summation, and that's what they're getting at here. All right. So how does that affect physical properties? Well, we're going to look at several properties: boiling point, melting point, and solubility. All right. So if you have a, let's look at let's arrange intermolecular forces, attractions between molecules from highest attraction to lowest attraction, right? Like we did last week. All right. If you've got ions and ions, that's the strongest attraction. If you've got, that's one molecule here, one molecule there. If you have one molecule that's an ion and the other molecule is not charged, but it does have a dipole, right? It has a slight unbalanced electron distribution. That's the next one. Then you have 2 molecules that are both dipoles. And there's a special case that's stronger than the average here, and that's hydrogen bonding. But the hydrogen bonding is a type of dipole-dipole. Okay. And then the weakest one you have is London dispersion. Okay. Now that we know the strength of these, and we also remember, let's see, we're going to talk about boiling point and melting point first. Okay. So when we discuss those physical properties of a substance, we're talking about a pure substance. So that means if all the molecule, if everything in the compound is ionic, right? Like you have sodium and chloride, then you're going to have the strongest attraction between those two, and the melting point is going to be extremely high, and the boiling point will be even higher.
Wow.
Because of the strength of the attraction of those ions. You have to heat them up very high. You got to get enough energy in there to break that bond. Right? That electrostatic attraction. If you have an ion and a dipole, the attraction is less. It's not as strong. So they will melt and boil at a lower temperature. It doesn't take as much energy to break it apart. Okay. For hydrogen bonding and dipole interactions, the melting point, boiling point is lower because the strength of the bonds, the intermolecular bonds, is less. And then these are the weakest. So their melting points and boiling points are right toward the floor. So what we're saying is that on this scale, both the melting point and the boiling point increase in this direction. So that should help you arrange, say if you're given molecules of certain types in a group and say, all right, arrange these in order of increasing melting point or decreasing melting point. Then you can ask yourself, all right, what types of bonds, what types of attractions are being experienced between any two molecules? Okay, that's what this table is all about.
So, well, I guess it kind of makes sense, but boiling point and melting point are related, whereas boiling point, freezing point are inversely related, right? We did a lot with boiling point and freezing point. We didn't do as much with melt.
Melting point, that's the same thing.
And boiling point?
Uh,
Or is freezing
no,
point?
freezing point.
Okay.
Freezing is going one direction, liquid to solid. Melting is going from solid to liquid.
But they're not inversely related.
Well, they happen at the same temperature, but they describe a different process, right? If you're going melting point, you're going from solid to liquid, and freezing point, you're going from a liquid to a solid. Now, in the melting point, you're adding energy. It's an endothermic process. And the freezing point is exothermic. You're extracting energy to get it to solidify. But it's exactly numerically the size of the value, not the sign. The sign tells you what direction. But the size of the value is the same for both of them. And boiling point, we rarely ever say anything else but boiling point. Right? But if we were consistent with these two, boiling point would be going from liquid to gas. And if you went from gas to liquid, that would be condensation. So condensation point. And they're both the same temperature. This has its temperature, this has its temperature. And the relationship to the strength of the intermolecular bonds is what determines those values. So when we look at this example, sodium methanoate. Now they're using a name here that we haven't studied. And they're using a compound, a carboxylic acid that's been made into a salt. So just take it for what it is right now. It is ionic, right? And it has a boiling point of greater than 250 degrees Celsius and a melting point of about 253. All right, so as it turns out, the boiling point and melting point here are relatively close together. We'll talk about solubility in a minute. Methanoic acid, right, is the formic acid is the one that top one was made from. Right? All you have to do is remove the hydrogen, makes it negative. Right? The hydrogen leaves and leaves its electrons behind. So now the oxygen is negative, and the hydrogen, we take the place of the hydrogen with a sodium ion. Okay, that's how it got there. But the middle one is the acid, and notice it has a boiling point much less than sodium methanoate, and a melting point a whole lot less.
Why is that?
Yeah, why is that? Well, the top one, let me just draw it. Is this a hydrogen? Yeah, this is a hydrogen. Okay, the top one, the bonds in this pure substance are ionic. We converted it into an ionic compound by removing that hydrogen and replacing it with a sodium. So now we have this ion attracted to that ion with the strongest attraction possible. So it takes a large amount of energy to break that bond. But if we go back to the condition before we removed the hydrogen, it would be like that. Now what we have is hydrogen bonding is available, and it's weaker than ion. Okay, so that explains why this one has a lower boiling point, a lower melting point than that one does.
Why are they so different though? Like we have 101(8).
Oh, why are they that far apart? I don't know. It's characteristic of that molecule.
Okay, I guess same thing with the one below it too.
Oh, ethanol?
Yeah.
Ethanol. Let's try to retain this. Yeah, let's keep the OH down here. They put the OH up top, but I want to keep it down here where this one is. And then we need a methyl group. So this one has 2 hydrogens and a methyl group up here. Okay, you still have hydrogen bonding available here. But what you also have is, and the term just flew out of my head. I'll try to explain it in a sentence. Oxygen is electronegative, very electronegative. So that's why you can get hydrogen bonding here. If you just focus on the OHs, like we do down here, this is going to be slightly negative and that's slightly positive, right? Okay. You would get a similar thing here, except that you have this oxygen up here that's also drawing electron density from that carbon. And this type of phenomenon will remove electron density from the third part, this 1, 2, and 3 away from it. It will still remove electron density. So this one is like, you know, bigger. It's a bigger electron density here in this acid versus this alcohol. Because that carbon is the same as that carbon, it's not going to draw anything. So that's the explanation for 78 boiling point versus 101, or minus 114 for melting point. Right? You got to get, wow, you got to get ethanol really cold for it to solidify. Remember that temperature, 78. Actually, I think it's 78.4 is the boiling point. if we ever get a chance to go in and do the lab, we're gonna distill, we're gonna fractionally distill ethanol from the wine, and I'm gonna have a thermometer in the top. So the vapor, when it comes up before it condenses, you can see what the temperature is. The temperature should be 78. Oh. Okay. Let's see. Did that one. Now this one. Oh, this is a continuation, isn't it? Ethanal. Ethanal is like ethanol, only now instead of a hydrogen attached to the oxygen, we took that hydrogen away and left the two electrons to make another bond with the carbon. So instead of doing, let's see. Like that. Yeah, like that. Then what we did was we took these two electrons, right? We put them right here in that bond. That took this hydrogen away. And now we have that. Ethanol. This is ethanol. This is ethanol. The reason it's ethanol is it's an aldehyde. Right? We haven't covered that yet.
So why did they put a double bond there? I guess because
Because this one needs 4 bonds.
oh, okay.
1, 2, 3, 4. It's got actually 2 hydrogens here. It's got 4 bonds here, needs 4 bonds here. And it needs 4 bonds to make the octet, right? Yep. Those things will get away from me.
Yeah.
All right. And does the temperature drops even further? Boiling point's lower. Melting point should be a little bit lower. Yeah, a little bit. Then when you get, let's see, dimethyl ether. I'm looking to see, no, it's not the same formula. Dimethyl ether is a symmetrical molecule. It's bent. And they're accurately showing that it's bent. And the reason it's bent is because that oxygen has 2 bonds here and it's still got those lone pairs. Right? So the dimethyl, methoxymethane. So they're saying this and this. So the longest chain is this one. So we're saying methane is the parent, and then methoxy is attached to it.
So this is kind of dumb. So why isn't there a double bond there? Because of
Here,
yeah.
well, if we did, we'd have to get rid of one of those hydrogens.
Oh, okay.
Yeah.
Okay, I think I understand now.
Yeah, there is a molecule like that.
Okay.
I'm sure. But it's bent and it's even less polar than the ones above it. And the boiling point, the melting point show it. It's dropping even further. If we have propene, all right. So we normally would have propane like that, 1, 2, 3. But instead, we're going to make one of those a double bond. Now instead of propane, it's propene. And what that also does is it aggregates extra electron density in that bond area, right? Which gives you the effect of some negativity there. So you still get that. And actually, we're dealing with London dispersion forces now. So you have more opportunity for electrons to instantaneously be distributed unevenly. And that adds to the attraction. Whereas if we, in the next one is propane, if we keep them all single bonds like that, you don't have those extra electrons. So the London dispersion forces are not as strong. And you can see it in the boiling point, melting point. Actually, they're pretty close together. They're not that different. And then there's ethane. Oh, there's one. Let's talk about London dispersion. I sort of alluded to it last time when I was talking about noble gases. The bigger the atom, the stronger the London dispersion. If you have more space, then you have more opportunity for uneven distribution of electron density, and that increases the forces of London dispersion. So as we go down in the periodic table, you get bigger atoms, and the boiling point and melting point go up.
And is that due to the, yes. But the center of the atom, and the electrons, the distance between those, there's less attraction.
It could, yes. Yeah,
But it is
that would have
related to
something,
that?
mhm. Right? The core, well, actually,
The core, yeah.
noble gases, they're all core, because it's complete shells everywhere. If you're going to talk about valence electrons for noble gases, you have to talk about the outer shell. It's got 8 valence electrons. Okay. But the core electrons are shielding those outer electrons from the effect of the protons in the nucleus. That's true. The shielding effect is real. And by doing that, it frees those electrons in the outer shells to move more freely, to be in places that they're not supposed to be, so to speak. Yeah, that's a good explanation for it. Okay, you also see a similarity there in the size of the molecule. If we have a homologous series, and I gave you a homologous series earlier, right? You have methane. These are hydrocarbons, right? And you have, ethane. You have propane, butane, pentane, hexane, and just keep going. The larger the molecule, the higher the boiling point and melting points. Because now you have more space for those electrons to become distributed. And I think we've got a slide coming up with also introduce the effect of branching. All right, there. Why is it? Are they in order? 5 types of intermolecular forces that are considered. No, they're not in order. But this is the correct order. Okay, so our example here is boiling water. Let's get that. These are ion-ion interactions. We've already hammered this one. If you can make an ion out of a molecule, then you have access to this type of attraction. Dipoles are obvious the way they attract. What's the question? Which compound has the higher melting point? All right. I'll come back to that one later, because I know there's a slide on it. Well, look at what types of forces are involved. Right. The first molecule is a sodium salt of ethanol, excuse me. So it would be like this. You'd have the sodium here. I need a new marker. You have the sodium there. You have the oxygen here that used to have a hydrogen on it. Now it's got a positive charge. And then you've got the The rest of the molecule,
Should be positive or negative charge on that oxygen.
negative.
Negative.
Yeah, did I say positive?
Yeah.
Okay, I meant negative. So we've converted that ethanol into a salt. And since it's ionic now, it has access to these types of bonds, and that would give it a higher melting point, higher boiling point. Whereas if we looked at this one, right there, the only thing it has access to is perhaps dipole. It doesn't have hydrogen bonding because there's nothing attached to the oxygen. So it's simply dipole-dipole interaction. You would have, let's see, like that, carbon, carbon, and then oxygen. And the dipole moment would be that direction, right, which would give you positive this side and negative that side. And that's the interaction that you would have with the other molecules. So this one should have the lower boiling point and melting point, and this should have the higher. We talked about hydrogen bonding already. You've got to have a nitrogen, an oxygen, or a fluorine attached to a hydrogen to give you that very significant dipole moment for the bond between the one atom and the hydrogen.
So you have to have a what again? I'm sorry.
Nitrogen, oxygen, or fluorine.
Okay.
Their electronegativity is high enough so that they extremely polarize the bond. But it's still a dipole interaction, dipole-dipole. It's just the strongest of the dipole-dipoles. Okay. Now, we've seen it with water, right? Because water's got two hydrogens on one oxygen, and it's a small molecule. But you can get hydrogen bonding activity on any part of a molecule that has this on it or this on it attached to something else. Actually, I don't know why we even put fluorine in there, because the only time you can do that, there's nothing else attached to it, because fluorine only forms one bond. Right? So hydrogen fluoride is the only possibility for fluorine and hydrogen bonding. But for nitrogen and oxygen, they can be attached to other things. So at any point on the molecule, if you have a group that has nitrogen attached to a hydrogen, and it could be two, let's see, if it's only one bond on this side, you could have another hydrogen over here, you know, along with its lone pair. Or if oxygen's only bound one on this side, you could have one, two, that's it. And you have two lone pairs. Well, what I'm trying to say is large molecules can have these OH or NH groups on them anywhere, and that will increase their dipole interactions with the solvent. Okay, we're going to get a rule of thumb in a second that helps us talk about solubility. All right. Okay, we're introducing a concept now in terms of hydrogen bond donors and acceptors. So when you look at a molecule that has, let's take methanol. Okay, this is going to be a hydrogen bond situation where you have negative here, positive there. So which one is the acceptor and which one's the donor for electrons or for the charge? This one would have excess, this would be deficient. So this one would act as an acceptor, this would act as a donor. So if we had, like that, lined up like this would be that, and you would form those attractions. So the, you know what, their terminology is backward from what I thought it would be. Hydrogen bond acceptor. All right, they're saying that this is the acceptor because it has the electrons, the electron density. Okay, they're referencing, the terminology is referencing the hydrogens. So who accepts the hydrogens? The oxygen accepts the hydrogen. That's the only thing that makes sense. The hydrogen bond acceptor is the one that accepts the hydrogen. Okay, so this is the acceptor. That oxygen. This is the acceptor. I'm trying to be consistent here. It's hard sometimes. Now that was for, this is methanol. Their example is ethanol. And if you have an extra, they're explaining this a little different than I did. Look at that one on the right-hand side, the formic acid. That oxygen attached to the carbon has the ability to with this electronegativity, draw electron density away from the carbon, which cascades to draw electron density away from the other oxygen. But the way they're looking at it is in terms of acceptors and donors. And they're not being consistent. The hydrogen bond you can't be an acceptor and a donor at the same time. So I think there's something wrong with that slide, don't you?
You know more than I do.
Yeah, I think there's something wrong with that slide.
I had some trouble when we were doing acids and bases, I was able to see it clearly in like a balanced equation, but looking at it in terms of this, I couldn't see like, oh, the proton has gone here or has left.
Mm-hmm.
I mean, I don't know how
Yeah.
this works. This looks tricky.
Yeah, I'm going to go with the hydrogen bond acceptor is the one that accepts the hydrogen. So that's both of those oxygens are acceptors. And the hydrogen bond donor is the H. Now, if they give me a better explanation, that whole group OH is donating the hydrogen. And this oxygen up here, it only has the ability as an acceptor. So if you interpret it that way, maybe that's what they were getting at. But it's not really that clear. So I got to be careful when I craft my questions for an exam to be consistent. Okay, what's the strength of the hydrogen bond? Well, it depends on the electronegativity of the oxygen versus nitrogen. Right? The electronegativity increases lower left to upper right in the periodic table. Or it increases from left to right if you're in the same period. Nitrogen is to the left of oxygen, so it's less electronegative. That means its hydrogen bond is going to be weaker. Correct? If nitrogen is less electronegative than oxygen, the potential hydrogen bonding is going to be weaker because the redistribution of electron density is less for an NH than it is for an OH. So that would affect the boiling point. And that's what this slide is trying to show. Right? Ethanamine is our analog for ethanol. The only thing that's changed is the oxygen's been replaced by a nitrogen. And when you do that, you get a different boiling point. In fact, for the ethanamine, the boiling point is a lot less. 17 degrees instead of 78. So ethane amine will boil at room temperature. Probably stinks too. Okay, London dispersion forces. Right, they're temporary, and that's what we're trying to show here. These guys are approaching each other right here. And as they do, the temporary instantaneous dipole on one of them affects the other one and causes it to produce a dipole, and then you get the attraction between positives and negatives. Okay. What are some trends? I was about to show you a trend of hydrocarbons, where the molecules that only have carbon and only have hydrogen in. And for our purposes, they're going to be straight chain to begin with. As you increase the number of carbons in your chain, you increase the melting points and the boiling points. Now, they only have access to London dispersion forces. So what that means, since they can only use London dispersion, that means the strength and the frequency of those London dispersion forces increase as the size of the molecule increases. So if you say, let's take propane. If you set it next to another propane molecule and one of them goes, say, slightly positive there, then this one's going to go attract electrons this way. It's going to be slightly positive on these ends. This one's going to be negative here and negative there. And this one, that induces a negative in this molecule. Then you get the attractions. Okay. Well, what happens if the molecule is bigger? It would just keep going. Say 1, 2, 3, 4, 5, 6. Add 6 more. Right. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is nonane. All right. We just keep going. So now what's going to happen? Now you get the potential for London's dispersion forces all down the chain. Increasing magnitude of London dispersion forces as the chain size increases. That is reflected in an increased boiling point and melting point. Right? That's why methane out of these gas taps is a gas. Right? You turn it on, it goes shh. Right? It's a gas at room temperature. Same thing for ethane or propane. Right? Propane's a liquid in the tank, but when you open it up and send it through the burner in your barbecue set, it turns to a gas really quick once you release the pressure. But once you get to butane and pentane is a liquid at room temperature. So is hexane, so is heptane. Octane is a liquid, but they have increasing boiling points. And you get up to, by the time you get to nonane, I bet it's going to be a solid at room temperature or a very viscous liquid. You're starting to get from octane is gasoline. You're going from octane to diesel fuel. When you get to diesel, it's a lot thicker. Have you ever seen diesel fuel? No, it's a lot thicker.
So,
I know it freezes in the winter, but
Yeah.
that's all I know.
Right, because it has a higher freezing point.
You gotta keep it like plugged up or something to keep it warm.
Mm-hmm. Yeah. You know somebody with a diesel car?
Truck, yeah.
A truck. Okay. Oh, yeah, yeah. And the other thing, I don't think it has anything to do with this, but the other thing is, if you've got a diesel vehicle, never run your tank dry because it will not prime.
Yeah.
It takes special, maybe even a mechanic to get it primed, so that you won't have a vapor lock in there between the tank and your engine, because once that line goes dry, it can't suck it up like it can with gasoline. It's too thick, I think. So you have to have somebody with a special tool to come in. You know what? I bet there's a port next to the tank, gas tank. And the mechanic will hook up a line and feed diesel fuel into it and fill up the line all the way to the carburetor. And then turn off the port and then you can start your engine. I bet that's the way they do it.
I'm no mechanic.
Yeah. That's the way I'd do it if I were a mechanic. Okay. So, what happens though when you branch? Say if we have 9 carbons, that's all we have going for us, 9 carbons. All right, let's start off with 9 carbons. And we take, say 3 of those carbons, like these 3 right here. Right? That means this carbon's gone, that carbon's gone, that carbon's gone. Like that. And we put those 3 carbons up here. Right, there's 1, 2, 3. 1, 2, 3. Now do we have 9 carbons? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we got the same number of carbons, but now you've got a branch. And the probability of the molecules laying close enough side by side to give you that same London effect is much less. So the attractive forces are decreased by branching. And you see that in the boiling point, melting point. Let's see, we have an example. Dimethylpropane. That's 1, 2, 3, 4, 5. 5 carbons in dimethylpropane. And pentane is 5 carbons, but it's straight chain. So its melting point is minus 130, but the melting point for it takes much less energy to melt it. Let me get my thing out of the way here. There we go. Let's look at boiling point. That'd be better. So the boiling point for dimethylpropane is a lot less than it is for pentane. They got the same number of carbons. It's just the branching is different. And you have weaker London dispersion forces with branch chains. The difference between dichlorine and diiodine. Iodine's a bigger atom, right? So diiodine is a bigger molecule than chlorine. You get that same effect that we had with the noble gases. The larger, the stronger the forces. So that's why the melting point and boiling points are higher for iodine than they are for chlorine. In fact, chlorine is a gas at room temperature. Bromine, the next one down, is a liquid at room temperature. And iodine is a solid at room temperature. And it's based upon size. Okay. Let's see. Oh, I've already talked about this. Right? We got the same number of carbons, but branching has had an effect on their boiling points. Right? The branched one has a lower boiling point. The forces holding those things together, the intermolecular attractions are weaker for the branched, so it takes less energy to boil it. That's why the boiling point is a lower temperature. Now we can talk about solubility. Right? Everybody knows the rule of thumb, right?
Or maybe.
About something being soluble in something else. Like dissolves like. Yeah. Now it's all clear. Right? Coming back to you. So what we mean by that is that polar compounds generally dissolve polar compounds. Polar solvents dissolve polar solutes. And nonpolar solvents dissolve nonpolar solutes. And as always in the sciences, there's gray area in between. So you get a certain amount of solubility even between vegetable oil and vinegar in your salad dressing, but it's not very much. These solubilities result from these intermolecular forces, these attractions between the solute and the solvent. We talked about that. Oh, you guys haven't had my first semester chemistry. I think we talked about that. Solvent and solute, or do you know what it means?
Yeah.
Okay.
I remember it.
Good, okay. So these substances tend not to form solutions if the intermolecular attractions in the pure substance, the solvent or the solute, are stronger than those that they would gain by forming a solution. In other words, there's nothing to be gained. If you have a polar solute and a non-polar solvent, because the attractive forces of the polar solute are so huge, it doesn't get any of the energy back that's expended to break it apart and make the solution.
I'm
Yeah.
just moving on something right now.
Oh,
Yeah.
okay.
Just so I have it.
I thought I was losing audience.
No, I'm listening. I'm just moving over here.
So I don't know if the general chemistry class you took explained it this way, but when you make a solution, you got a solute and a solvent. And in terms of energy, you want to end up with a solution. And first thing you have to do is to get those solute molecules apart. So you got to put energy into it, right? There's your enthalpy. You got to put energy in. So this is endothermic. You got to break them apart, break those bonds. Same thing for the solvent, right? This delta H is positive. Sometimes we call that make a hole. Once you get them apart and you put them together, then what's the attractive force between the two? Well, there's going to be some attraction, and that would make delta H negative, right? Exothermic. It's going to give up some energy. The balance between the energy you had to put in and the energy you get back determines whether they will solubilize. If it takes a whole lot of energy to get them apart, but you get nothing back, then it's unlikely that you'll form a solution. Or if you do form a solution, it's going to be cold. It's going to be overall endothermic, right? Because this is huge, huge, very small. So the balance is endothermic. But if these are both nonpolar, let's say, no. If I already did polar and nonpolar, right? It takes a little bit of energy to break them apart here because they only have London dispersion forces to hold them together. This one has much stronger forces. So you put a lot of energy in here, a little in there. What do you get back here? Well, polar and nonpolar, I mean, they still have London dispersion forces. That's all they've got because that's nonpolar. So you don't get much back. And the balance then is going to be, you have to put a lot of energy in to get your solution. Now you can do that. Right? Have you ever seen an engine steam clean? Right? You have a steam generator under high pressure and a guy's wearing his protective stuff and big gauntlet gloves, and he's got his steam wand. And he's in there getting the grease off your engine. Now, some of that effect is it heats the oil up so that it runs. It's runnier. It reduces the viscosity. And the force of the blast blows it off. But if you look at the chemistry of what's happening, that hot steam, hot water, hot steam, is actually dissolving the oil. It's solubilizing oil because there is sufficient energy in there to overcome the differences between the polar and the nonpolar. Okay, so let's see if they've got us given us a rule of thumb here that we can actually use. Let's see. Solubility is a result of an increase in entropy provides the driving force for two substances to mix. Okay, now we're getting away from enthalpy and we're talking entropy. Remember entropy?
Yes, we just finished talking about.
Entropy. Delta S.
Yeah.
Okay. The simplest way to think of entropy is disorder. The higher the value for delta S, the more disordered. And the condition of the universe overall, the whole universe, is that entropy is increasing always. So everything happening in the universe taken together, delta S is positive. It's increasing. But it can happen on a local level. It can be positive or negative, depending on the interaction between one system and its surroundings. Okay. But the desirable state for the system, in this case, when we're making a solution, the desirable state is to increase the entropy. You want more microstates available. Now we're talking statistics. More possible microstates means increase in entropy or an increase in disorder. Okay, is that going to happen? If it does happen, then you get a solution. If it doesn't happen, you don't get a solution. So I think where they're going with this, let me see. Let me read and be sure that that's where they're going with it. They don't mention entropy there. They don't mention entropy there. All right, so I'm free to say what I want. When you put these two substances together, the solute and the solvent, do they want to associate with one another or not? If they form a solution, they do want to associate with one another. And when you put this volume into that volume, it gives you more volume. And by associating with one another, you have both have access to more volume, which increases their entropy. That's the way I look at it. Whereas if they don't associate with one another, like oil and water, then the oil, let's say this is oil. The oil is stuck in its previous volume of the oil, and water, volume of the water. They separate, and that does not increase their entropy, because now the water still has the same volume. It's got this roughly the same number of microstates. The delta S is not increasing. And the same for the oil. But by making a solution, you give each party access to more microstates. Okay, water and hexane. I think we're going to run out of time. We have to do our lab next week. So when that happens, when we have to do it, we may not even have time next week because we got a lot to do next week. Don't we have an exam? Yeah, we have an exam. Well, we'll shift our labs down, right? Ratchet them down. And as soon as we get time, we'll have a lab. That just means I'll have to, a couple of things I'll have to bring back with me. I'll take the wine bottle with me so somebody around here doesn't find it and drink it. And I'll have to bring fresh ice too. Okay. So the, let's see, water and hexane. Hexane is nonpolar, right? It has access to London dispersion forces only. Whereas water is a hydrogen bonding molecule. It has access to London dispersion too, but they're so weak, they really don't matter. The dominant forces in water are hydrogen bonding. So when you try to put them together, and get the induced dipole and induced dipole interaction, we can't use the hydrogen bonding of water because, well, okay, it's a competition, right? In order to form the solution, the water molecules have to associate with the hexane molecules. But the bonds, the strength of the bonds for one water molecule with the other are still there, even though you're trying to mix them together. And what they do is they segregate, chemically segregate from one another, right? It's like no blacks allowed, or blacks have to drink from this fountain, or whites only in this bathroom. Right? They segregate because the strength of the bonds between the water molecules are so much stronger than hydrogen bond than London dispersion, that the water thinks to itself, if I may anthropomorphize, the water thinks to itself, why should I waste my time with hexane? I've got water molecules here that are perfectly willing to bond strongly with me. So it does. And you don't get a solution with hexane in water. Whereas if you have hydrogen bonding available with ethanol, right, you've got that OH group on the end, now you've got the ability to hydrogen bond with the solute. And that does form a solution. Okay. The same goes for ions, ionic compounds, and polar solvents. Up to a point. Remember the ionic compounds that are insoluble in water, right? You had I don't know, if you were a chemistry major, you have to memorize the list. But with my class, I give them a chart. And you say, here's the cations across here, here's the anions down this way, find out where they meet, and look at the box. Is it clear or gray? If it's gray, they precipitate. Right? That combination of cation and anion will not dissolve in water. Now, there are various explanations for that, but I've already wasted enough time as it is. But for the most part, ionic solids dissolve in polar solvents. Most of them. Not all of them, but a large portion of them do. Because you get that positive-negative attraction. Now, when they actually do go into solution, they go through a process called solvation. And it's kind of like water molecules attack the compound. And if it's an ionic compound, in this case, we've got the anion being surrounded by water molecules facing their positive charges. And the sodium ion is surrounded by water molecules with their negative charges. And the pictures only show one sodium ion and one anion. But beyond that, there's a whole lot more. There could be on the other side of these, let's see, sigma, it's too small. On the other side of these water molecules, they're going to be negative. So they would be attracted to the sodium. So they can participate in solvation of multiple components. And the water molecules are attracting each other too. Okay, in which solvent would you expect sodium chloride to be more soluble, diethyl ether or propanol? Well, sodium chloride is ionic. So what possibilities do you have with diethyl ether? Primarily, diethyl ether is going to be like that. That doesn't tell the whole story because you've got hydrogens here and you've got hydrogens here. You've got some steric problems there. But that's a nonpolar molecule overall. And you've got these big groups out here that kind of restrict the ability of getting to the oxygen as a hydrogen bonding donor. So You've got ions and nonpolar. So the diethyl ether is probably not going to dissolve sodium chloride. Propanol, on the other hand, let's see. Like that. Propanol has this ability to become slightly negative and slightly positive. So you get some polar action here that can attract sodium and chloride ions. The sodium would be attracted to this side. The chloride would be attracted to this side. So I think propanol would be a better solvent. It's not the perfect solvent, but it'd be better. Okay. When we look at functional groups and how they influence the solubility of compound. Small alcohols like methanol and ethanol and propanol are relatively soluble in water. They're called hydrophilic. But as the alcohols get bigger and bigger and bigger, they become less soluble. Because now you've only got that one OH on the end, and you got this nonpolar tail sticking out there. And it doesn't like water. The example that they've given you here is sucrose. And that's drawn the left-hand side of that molecule is glucose, and the right-hand side is fructose. So fructose forms a 5-membered ring, glucose forms a 6-membered ring, but the 6-membered ring has an oxygen in it. Right? And so does the 5-membered ring. So actually, glucose only has 5 carbons in the ring, and then 1 carbon outside the ring. See it in the back with the OH on it. But the point here is not to labor over the representation. We'll get to that later. Is to look at all the OHs sticking out of those molecules. Right? Potential for hydrogen bonding there. Huge potential. Right? Let's see. How many OHs do we have? 1, 2, 3, 4, 5, 6, 7, 8. We got 8 OHs on just that one molecule. And that gives you a huge potential for hydrogen bonding. Especially if the solvent is water. All right. Okay, here's our rule of thumb for solubility of carbon compounds that have hydrophilic functional groups. So we're going to focus on the alcohols, just for convenience. So look, how many hydrophilic functional groups do you have? And then how many carbon atoms do you have? Well, in methanol, you've got 1 alcohol group and 1 carbon. That's a 1-to-1 ratio. That would be soluble in water. Ethanol has a 2-to-1, 2 carbons and 1 oxygen group, alcohol group. So that's still soluble. Propanol, propane 1-ol, has 1, 2, 3, and 1. So 3-to-1 is the breaking line. Propanol is still soluble in water. But when you get to butanol, now you got 4 carbons and 1 hydroxyl. That's a ratio of 4-to-1, and it's only slightly soluble. Right? Solubility is decreasing as we increase the number of carbons. And you get to the point where you have heptane 1-ol, it's almost insoluble. So if we look at this one, would you expect each of the following compounds to be soluble in water? Why or why not? Okay, what we need to do here is consider the solvent. The solvent is polar. Right? So what we need is a polar situation. So do we have polarity on any of these molecules? Yeah, they've all got OH groups. Okay. Then we look to that rule of thumb. what is the ratio of carbons to the polar groups? Well, for A, let's see, we've got molecules A, B, and C. For A, let's count up the carbons. Let's see. 1, 2, 3, 4, 5, 6. We got 6 carbons. 6 carbons. And 2 hydrophilic groups. So that's 3 to 1, right? So that should be soluble. That particular alcohol. It's a diol. The other one is a cyclohexanol, right? So how many carbons you got there? 1, 2, 3, 4, 5, 6 to 1. 6 to 1. That's not soluble. This one's soluble. That one's not soluble. Because the ratio of carbon to the OHs is too high. And then 2-naphthol is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That one's 10 to 1. That's not soluble. So the only one that's soluble here is A.
Can you explain one or A one more time?
Yeah, I counted up the number of carbons.
Okay.
Okay, 1, 2, 3, 4, 5. Yeah, 6 of them.
Yeah.
And then the number of hydrogen bonding groups or polar groups. Let's just say polar groups.
Yeah.
They don't have to be hydrogen bonding. Polar groups. There are 2 of them, OHs, 2 OHs, 6 carbons, and the ratio is 3 to 1. 6 to 2 is 3 to 1.
Okay, so pretty much anything you can deduce down.
Yeah, 3 to
Okay.
1, 3 to 1 or less will give you solubility in water. Yeah, that was the rule of thumb on the page before, right here.
So let's say it was like 12 and 8. Would it then be correct?
12 and 8.
So that would
Yeah.
reduce down to 6 and 2, right? Right?
6 and 2. 3 to 1.
Yeah.
Mhm.
Okay. All right. I think I understand.
That's just a helpful rule of thumb to determine solubility, rough solubility. And here's the author's explanation for it. I'll leave it up long enough to get recorded. Okay, this one's a little more involved. If we have these 1, 2, 3, 4, 5, 6, 7 compounds. Get this up out of the way. Let's go there. There we go. These 7 compounds, we want to rank them in order of boiling point, melting points, or solubilities of a set of compounds. So if the forces of attraction are higher, you're going to get a higher boiling point, a higher melting point, and the solubilities, well, they don't tell us what the solvent is. Do we assume it's water? Let's see what the explanation is, and that may tell us. Identify the most important intermolecular interactions in each pure compound and group them together. Okay, we'll do that. All right, so let's group them together. A, B, C, D, E, E, F, G. Okay, A. That is toluene. In other words, it's a benzene ring with a methyl group on it. That's completely nonpolar. All right, so we're going to put A in the nonpolar group. Okay, are there any that are like it? Well, let's see. D is benzene. It's definitely nonpolar. All right, so A and D are nonpolar, and G is also nonpolar because the chlorines, even though the bonds between those chlorines and the carbons are polar, they're directly opposite one another, and they cancel out. So G is part of the nonpolar group. Okay. Now, do we have any that have access to hydrogen bonding? I could use this one and this hydrogen bonding. B, right?
Yeah.
B is available for hydrogen bonding,
And then E.
and E. And that's it. That's all the hydrogen bond. So these are going to be London dispersion forces only. These are going to be London plus hydrogen bonding. Are there any that are actually polar that will have dipole interaction? Oh, wait a minute. I left out F. Oh, yeah, F. Yeah, F is nonpolar because those methyl groups don't add anything to its polarity. So what do we got left? B and C. So,
Or C.
excuse me. B, C is by itself. Okay, what is C? Ah, okay. So now we have a benzene ring. We have dipole. Overall dipole for the molecule. Because those chlorines now have polarized their bonds and they're both pointing in generally the same direction. So when you add them together, you get a polar molecule. Okay. Let's see. Within each group, relative boiling point's the same overall order. Okay, so there are the nonpolars. Let's see if I got them right. A, D, F, and G. Okay. And then C is dipole, and B and E are hydrogen bond. Okay. So if we're going boiling point increasing from left to right, the boiling point would increase from A, D, F, and G. Boiling point would be less than the dipole and less than the B and E. Okay. That's general grouping. Now we need to go into the groups and see if there's any differences among them. Let's start with the easy one. These two. All right, which one has more? Yeah, which one has more hydrogen bonding potential? E. So E is going to be a higher boiling point than B. There we go. Now we got to figure out these guys right here. The least polar of all of these would be benzene. Because all it has around it is hydrogens.
So D.
So that would be D. Right? So D would be the least. The most would probably be G. Because it still has those polar bonds. So there's going to be some positive negative interaction there. So what was that? G? G. G goes here. Okay. Now we have to define A and F.
I'm assuming A is right before D and then F.
Wait, did I put the wrong one in there? No, this one.
Yeah.
And we can also base it upon
Right after, I'm sorry.
size of the molecule. Right? If it's London dispersion, then the size matters. So this benzene is the smallest one. Then the next largest one is A. And the next largest one is F. So that should be the order.
So is the reason why G is bigger than F is because the chlorine?
Yes.
Okay.
Yes. Okay. Now they're going to give us the answers to see if I'm right. D, A, F, G, C, B, E. Okay. At least I agree with the author.
It has A being weaker than D.
I'm sorry.
It has A being weaker than D. Or, I mean, I don't know if it's in order.
On that slide?
Yeah. Wait, no, it's on slide 48, so right above that one.
That one?
Yeah, there we go.
Oh, when they're in their groups,
Yeah.
in the separate groups, they haven't been ordered yet.
Oh, okay, so, okay.
Yeah.
I understand now.
We sort of, we put them into, it's like sorting the mail. You put zip codes together over here, 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 and then you go into each bond and order them by your route. So that's what we did here. Okay, what's this one? Rank from lowest solubility in hexane to, let me get my picture out of the way. Highest solubility in hexane. Lowest to highest solubility in hexane. All right. So we got A, B, C, D, and E. And the solvent is hexane. Right? Completely non-polar. All right, so what's A? A is an ether. B is an alcohol. C is a diol. In other words, double alcohol. D is an alkane. And E is a ketone. Right, it has, actually that's acetone. It has methyl group here, bound to a carbon, which has a carbonyl group on it. Okay, so we're going from lowest to highest. The least soluble is going to be the one that's most polar, because this is completely non-polar. So the most polar one, I would think, is going to be C, this diode. So it's the least solubility. So it's going to be C is the least soluble. The next least soluble should be the other alcohol, B. Okay, so we got those. Then the acetone, the ketone, will have some polarity to that bond because oxygen's electronegativity. So I would put it next. Okay. Then we got to decide between the alkane and the ether. Ether's got that oxygen in there. And it is going to introduce some polarity, even though overall it's balanced. But you still got the negative concentration around the oxygen. So I think ether's going to be next. And the last one, the most soluble, is the alkane. 1, 2, 3, 4. 1, 2, 3, 4, 5. The pentane. Okay.
So I'm getting like all these right just based off looks. Is that what I should not do?
Just off looks.
Yeah, just by looking at them.
Yeah.
Okay.
I mean,
I didn't know if there was like more of a way to reduce it down. Like, because I don't want to look at it and then get something more complex and that looking at it isn't good enough. Does that make sense?
yeah, we're focusing on the fundamentals of solubility. What makes things soluble in something else? Look at the solvent, right? It's completely nonpolar. So then you look at the solutes, the potential solutes, and you look at their polarity. What type of intermolecular interactions can they have? Well, if they're like this one, right, London dispersion only, they will be extremely soluble. And that's alkane. It's a straight chain, carbons. No polarity there at all. So it should be the most soluble. And then you look at the other, if you have any other elements attached, then they will contribute to any types of polarity. The one thing that we haven't done here is branching. Branching of a straight chain into a branch with the same number of carbons is going to reduce the the London force interactions. So a branched should be less soluble than a straight chain. Now, let me see if they make a liar out of me. Okay. In order. C, B, E, A, and D. Okay, so we got it right. At least on that simple scenario. Now we're going to sort of break a little bit and talk about solvents. In organic chemistry, we generally divide solvents into two types: protic solvents and aprotic or non-protic solvents. What we're talking about here is a protic solvent is one that has hydrogen bonding potential, like water, or a solvent like ethanol. Okay, a non-protic, perfect example would be hexane, right? There's no possibility for hydrogen bonding there at all. The example that's given here is DMSO, which is short for dimethyl sulfoxide, which looks like this. Oops. Sulfur. Like that. So these are methyl groups, dimethyl sulfoxide. That's DMSO. And it's an example of an aprotic solvent. There's no hydrogen bonding there at all. It might be slightly polar. Actually, it's not going to be that polar because sulfur and oxygen are very close to each other. Right? It may not be polar at all. Or if it is, it's not very much. So it's reduced polarity. And we demonstrate its polarity by solubility. Right? Sodium chloride goes into water at 35 grams per 100 milliliters of water. That's a lot. But DMSO, you can only get 0.4 grams of sodium chloride in that one. So that gives us an indication about the you know what? There's more to this story than that. Why do I say that? Because the authors are telling us that the dipole moment for DMSO is greater than the dipole moment for water. Water is 1.9 and DMSO is 4.0. So there's something else going on here. All right, let's see what it is. Well, there's the solvation trick. For one thing, when water approaches a cation or an anion, you can get a lot of water molecules surrounding that cation or anion. A lot of them, they're packing there close. So you got a whole lot of force being applied to one ion. Whereas DMSO is a bigger molecule, right? It's got these methyl groups sticking out here. And you get fewer surrounding the ions, which means you don't have as much force of attraction. Right? This is going to be slightly negative, right? Because it's above sulfur. Right? Above and to the right is more electronegative. So we do have a dipole that way. And the reason you can only get just a few surrounding those ions is that steric interference. You got these huge methyl groups right here. And they're interfering with an approach to that positive. So since we're talking about the solubility of sodium chloride, this is the positive, and chloride is supposed to come in here and associate with that. But chloride is a big ion, and you got all this mess in the way. Steric interference keeps the chloride away, further away from that positive. I mean, it's still in the neighborhood, right? But it's further away, and distance, it matters. The further away two opposite charges are, the smaller the force. It's like that gravity, right? Further away two bodies are, the weaker the force. So we've got a situation of steric hindrance. That's the proper term. And steric hindrance plays into organic chemistry in a major way. Okay, these are examples of protic and aprotic solvents. The protic solvents, water, ethanol, right? Acetic acid, They all have the potential for hydrogen bonding. Whereas an aprotic solvent doesn't. DMSO is at the top of the list. Propanone or acetone is an aprotic solvent. And N,N-dimethylformamide. What it does is it substitutes, let's see, how does that work? Well, it's got the carbonyl group and it's got the substituted amine group. So is that a primary, secondary, or tertiary nitrogen?
Repeat it again.
Is that a primary, secondary, or tertiary nitrogen in that last one on the lower right?
Tertiary.
Uh-huh. It has 3 bonds with its carbons. Okay. So that's going to give you a huge steric interference, right? Those methyl groups out there will get in the way. All right. Let's see. How many more slides do I have?
We're on 57 right now. So
Okay. And I think it goes into the 60s, doesn't it?
65.
Okay. All right. We mentioned last week that in biochemistry, there were basically 4 groups. You could take all biological molecules and pigeonhole them into 4 groups. Right? Remember those? Nucleic acids, which are essentially RNA and DNA, right, for transferring information from cell to cell, or from mother to daughter, actually. And then proteins and carbohydrates and then lipids. Now these 3 are well defined based upon their chemical composition. Right? They're different because of that. These are nitrogenous bases. These are amino acid polymers. These are polymers of simple sugars like glucose and galactose and fructose and all those just chained together. But the lipids are defined based upon their solubility in water. They are insoluble in water, and they can have one of several types of structures. And that's what's referenced at the bottom of that slide, right? You can have, we used to call it true fats. That's what we called it in anatomy and physiology. And a true fat is a triglyceride of glycerol. Right, remember that? Okay. Another type of lipid is a phospholipid. And a phospholipid simply has a phosphate group attached to it somewhere. It could be a long chain attached with a phosphate. It could be a true fat where one of the fatty acids has been removed and replaced by a phosphate. Steroids, they have a complex heterocyclic structure, fused rings. I can't reliably draw it right now, but we'll probably get a picture of it later. Steroids and waxes. I do know what a wax is. A wax is a combination of a long chain acid with a long chain alcohol. So we form that bond with this carbon, and it's all straight chain carbons with hydrogens on them. That's the alcohol. This is the acid. And when you form that bond between these 2 carbons, one of the products you get is water. And that's a wax, chemically speaking. Right? So true fats can either be, let's see, they can be oils. They can be, what's the other term I'm looking for? Well, fats and oils. They could be solid at room temperature, right? Like lard. There you go. Lard or soybean oil. Or actually, what's popular now is that all I can think is it's made from rapeseed. I can't remember the proper name. Never mind. It's from the mustard plant, mustard group. Anyway, lipids are insoluble in water. That's their defining characteristic. Fats can come from anywhere. They can come from animals. They can come from plants. Actually, I think you can get some fats from microorganisms. If they're liquid at room temperature, then we call them oils. So that's operationally defined. And their primary purpose is to store energy. Okay, so when you have this glycerol molecule and you have a fatty acid attached to it, let's see, it's going to be that with long chain carbon. And let's see, there's an oxygen there, and this is going to have an oxygen there. And let's see, what does that do? It's 1, 2. We put on this side, 4, and then we have oxygen here and there. So we have 3 fatty acids. But these are fatty acids. Let's see if I got that right. 1, 2, 3. 1, 2, 3, 4. Yeah, okay. So, what are we going to do when we make soap? We're going to hit it with base, sodium hydroxide, lye. And it's going to break this bond right here by introducing the hydroxyl. And when it breaks the bond, what it leaves behind is that's an alcohol, and this becomes like that. So we need the counter ion from sodium hydroxide, right? The hydroxide ends up over here. The sodium ends up as a counter ion to the fatty acid. Okay. So I said all that to say this. Once these are released, then the enzyme systems in your cells, if you need it, can break off parts of this molecule. Actually, they break off 2 carbons at a time. They start working here. They take this carbon and that carbon, break them off, and they go into, let's see, where do they go? They go into the Krebs cycle. You'll learn about that in the biochemistry. They go in, they are inserted into the Krebs cycle, and that generates energy. That's an aerobic. That's an aerobic reaction sequence. Okay, so they're energy storage mechanisms. They contain huge amounts of energy available to the cell. By the way, let's see, if you're in nutrition and exercise and sports and that type of thing, when your body needs energy, where does it go first? Before that.
Oh, what are you talking about? What's this?
Yeah, ATP.
It goes to ATP first, sometimes GTP. It depends on the tissue, but that's where it goes first. And as it runs out of that, which happens really quick, it has to replace that. Then it goes to simple. It goes to simple sugars. Yeah. So let's just keep it simple and say glucose. So then your body tries to flood the system with glucose. Where does it get the glucose? Yeah, good answer. It gets glucose from carbohydrates, starch. Now, there are two types of starches. There's plant starch and there's animal starch. Animal starch is glycogen. And it's based upon the same subunits. The glucose subunits are hooked together in these polymers. But for plant carbohydrates or starches, they're straight chain, most of them. But for animal cells, we store carbohydrates as glycogen, which is highly branched. Okay, but they're easy to remove the sugar and flood your system with it if you need it. That's why marathon runners the day before, or a couple of days before, they start gorging on carbos. Yeah. They get as much of that in their system as they can. And the excess goes where? The excess goes to fats for long-term storage. And then if you're a marathon runner, eventually you're gonna use up definitely that, and you're gonna go to fats. So the efficiency of your body in converting fats into energy is one of the conditions for a good marathoner. The other is the type of muscle twitchers you have. Yeah, faster or slow.
Slow
Yeah.
or light or dark.
Uh-huh. But that's the order that the cells go for energy. Go in that order. So if you're trying to lose weight, right, you got excess fat like I do, then you got to burn up your carbohydrates to the point where your body has to go to fats. Right? So if I exercise for like 30 seconds, that's not going to get rid of any fats. I got to go. My physical therapist now has me on what they call the new step. Right? It exercises both your legs and your arms. You're sitting down. I had me go for 15 minutes on that thing. And I am sweating when I'm finished. Okay. So fatty acids, those are examples of fatty acids. And I'm not going to have you memorize those because if you're going to biochemistry, you'll get it then. Right. Just know that the convention for naming fatty acids is a little bit different than what we're learning for general organic chemistry. Right. In fact, all of biochemistry is a little bit wonky, right, with their naming convention because they got such a wide variety of molecules, biological origin molecules that they have to deal with. How do you name them? Right? If you name them the way organic chemists name theirs, you're going to have a name for every molecule that's as big as this table. So they identify which ones are most common and give them a parent structure, and then they work from that. So when we say unsaturated fatty acid, what do we mean?
Not solid. Like it's a liquid at room temperature.
That's one of the physical properties, yes.
So, but we're talking about
Right. Why is it that way?
the way they lay.
Yeah, yeah. And they lay that way differently because of the double bonds. Yeah. When you get down to oleic acid there, a third from the bottom, you introduce one double bond. And notice instead of being perfect zigzag, it flattens out and starts zigzagging again on the other side. What that does, it puts a kink. It's shown straight there, but when you actually build a molecule, it kinks. And that makes those attractive forces less.
Making it, would that make it saturated?
No. Saturation means they're all single bonds. Right. So lauric acid, palmitic acid, stearic acid in that list, they're all saturated.
And that is because they can lay so tightly
Mhm.
together.
Mm-hmm. And then linoleic has two bonds that are double bonds. So what happens is, restaurant operators want an oil that will stand up to continuous use, hot conditions for a long time. The problem is with these double bonds, they're more reactive. So if you get oxygen in the vicinity, oxygen's going to attack those double bonds, and that causes rancidity. So what they want is saturated fatty acids, or a high percentage of saturated, because they have a higher boiling point, a higher melting point, and they stand up against the attacks of oxygen. The problem is the manufacturers who take unsaturated sources and convert them to saturated, they produce a certain type of double bond arrangement that's not natural. It does not occur in any living system. Yeah, by adding hydrogen to it.
Now, they're not allowed to do that in modern art. What was that called? It used to be a thing that you could see on a nutrition label. Because it was like man-made, it was good for shelf life and things of that sort.
Uh-huh.
But it's not allowed anymore,
What, the labeling or the product?
the product, like you're saying, it was adding hydrogen to it, but I don't know what it.
Oh, the partially hydrogenated vegetable oil?
No, it was.
No. You'll think of it.
Trans?
Huh?
It was,
Oh, trans fat. Yeah,
and that was that's adding the hydrogen.
yeah, we haven't talked about cis versus trans yet. All of these naturally occurring fatty acids, where they're unsaturated, they're cis. In other words, the long part of the molecule on either side of that double bond is on the same side of the molecule. Whereas when you hydrogenate it, the chemistry that's involved there always produces trans. So the one long end is on this side, the other long end is on this side of that double bond. That's trans. There's our triglycerides. Let's see, did I do it right? Oh, here it is. Yeah, they're supposed to be like that. I left that part out. That's where this one comes from. And then when you saponify that fat, you get those fatty acids, sodium salts. Now, when you actually make soap, you use enough lye so that all of the fat is saponified. But that usually means you have an excess of sodium hydroxide in there. So that's why Granny on the not the real McCoys, Clampett, yeah, Beverly Hillbillies. Yeah, why Granny would wash Ellie Mae's hair with her homemade soap, and then she'd get rainwater and rinse it to get rid of all that sodium hydroxide that was left over. Otherwise, it would destroy her hair. So you have to rinse with rainwater, which is distilled water. Now, some people that are really good at it, they can reduce the amount of excess lye in their product so that it's not irritating. And the only way to tell for sure is to test the pH. Let's see. Sodium hydroxide and the acid. It should still be basic. But if you have a significant amount of sodium hydroxide in there, the pH is going to be it's going to be like 12. But if you have a reduced amount of sodium hydroxide left over, then you're just depending upon the sodium salt of the fatty acid. Then your pH is going to be in the neighborhood of maybe 8. Yeah, I'm running out of time. We're going to have to skip the lab today. Right? We only go to what? 1:30?
Yeah.
Mhm. A phospholipid consists of glycerol backbone attached to 2 fatty acids. Okay, so here's an example. If you take the triglyceride, and instead of a fatty acid, you substitute a phosphate group, then you get a phospholipid. And that can be used to make all kinds of other things. Right? The other side of that phosphate acts as a bridge in this case. It bridges to a quaternary amine. Right? Because see, you got 4 bonds coming off of that nitrogen. That's a quaternary amine. Phosphatidylcholine. That's a fairly significant molecule in cell biology. Okay. Now, what else can you do with these phospholipids? You can make a cell membrane out of them. The basic structure of cell membranes in eukaryotes, right? Not prokaryotes like bacteria, but eukaryotes definitely have, well, I shouldn't say that. Prokaryotes have a special way of doing things. But this phospholipid bilayer, what it does is it faces outward, away from the cell and inward to the cell, the aqueous media. It points the phosphate side of the molecule because that's water, that's hydrophilic. And then the tails, the long hydrophobic tails, dissolve in each other on the inside of the membrane. And then what you do is the membrane is pockmarked with all kinds of things, enzymes, channels for movement of ions and simple molecules across the membrane. That way the cell can control what gets in and out. You have markers that are attached to the surface that signal your system, I'm friend or I'm foe. So if it signals I'm foe, then your immune system kicks in, right? And they go attack that, whatever that cell is. That's the problem with some autoimmune diseases, right? We get those signal molecules on our cells that our body mistakes for foreigners, right? And for people with, I don't know, lupus or rheumatoid arthritis, as 2 examples, their own bodies are attacking their system. Okay, so the phospholipid bilayer is the foundation for the cell membrane. There's your steroids. This is the basic structure, these 4 fused rings. If you have a ring that's sharing 2 carbons, it's fused. Say if it went like this and like that, like that, like that, these 2 rings are fused because they both share that carbon and that carbon.
But there's only 1 carbon there, correct?
Yes, just 1
Okay.
carbon. Right, right. That's true. But that's the basic structure of steroids. And things like cholesterol, testosterone, for example, aldosterone for controlling blood pressure, cortisone for treating inflammatory conditions. Actually, cortisone is not produced in the body. Right? We make that outside and inject it, and it has the effect of reducing inflammation. So there you see the basic ring structure, and then the differences among those molecules are just the side groups. And this is one of those cases where biochemists have agreed upon cholesterol is that structure and no other. Okay. Then they know, and they don't have to go through that mile-long name that organic chemists would have to use. Okay. Waxes. Okay. Bees use waxes to make their combs. Right. What does a honeybee do when they're building a honeycomb? Not the brood comb where they put the little babies, but the one where they store honey.
You talking about like the hexagon shape?
Yeah, they make the hexagon shape. Uh-huh. And then they've gone out to a flower and collected nectar. Yeah, which is largely sucrose. Doesn't have to be, but most of the time it is. And then they bring it back. It's in their stomach, and they spit it in there into that comb, and they do one last thing before they seal it up.
They wax it, I think.
No, before they wax it over,
Uh,
they spit. They spit in your honey because their saliva contains an enzyme called invertase. And what invertase does is it cracks the bond between that double sugar, and it separates the glucose from the fructose. Now, let's see. We haven't talked about this yet. Colligative properties. That comes later in second semester. But the fact is, if you increase the number of moles of particles in your solution, you increase the osmotic pressure, and you increase the boiling point and decrease the freezing point. So it actually acts as a preservative, because if the osmotic pressure is high enough, invading fungal and bacterial cells can't live. They're completely dehydrated when they get in there. So spitting is necessary. Okay, that's beeswax. Let's see, where else do you get it? Oh, lanolin off of sheep sheared. Extract the lanolin from sheep wool. And then you got waxes in your ear.